Hello everyone. In this session, I would be talking about the different algorithms that are used for building classification trees. Classification trees are the response variable is a categorical variable. If the response variable is a numerical variable, we have already said that they come under the regression trees. So because this is a classification tree, I can very well assume that the response variable is a categorical variable. But within that categorical variable, I may have, in some cases, there could be only two categories which I may have to predict. In that case, it's typically a binary variable, whereas in some cases, there could be multiple categories to which a data can belong to. So here we are looking at those specific algorithms where I'm trying to group the data into more than two categories, right? Or probably these methods are applicable even for binary or in some cases for more than two categories as well, right? So in this example that I'm going to take up, I'll take one data set and we'll go through the entire process, try building the tree with different algorithms. So here I am going to talk about 5 different algorithms in the whole process which are implemented in different R packages. So we would be implementing 5 different algorithms and use them to really assess the accuracy of the model, right? So we will get started with the modeling wherein we are trying to find the relationship of a categorical response variable, linking them with the various explanatory variables. One or more explanatory variables are typically the attributes, and what we see is these attributes could be either numerical or categorical in nature. So here I'm trying to bring in 5 different algorithms in this session. One is a preliminary classification tree, the very basic, the concept of classification tree. Then we'll talk about the most popularly used mechanism, which is C5.0 classification tree. Right, the algorithm that we are going to talk about is the C5.0 algorithm. Remember, in all these things, I'm not talking about the mathematics behind each of these algorithms, right? I would be more focused on the business aspect of each of these algorithms. How are they typical? What should be the input that I have to give in the R code? Whatever is the output that I get from R, how do I really interpret the output? How do I use this model for prediction purpose? Whatever the model has predicted, how do I really assess the accuracy of the model? And if at all I have to compare between the two models, how do I get into the comparison process? And I would also look at what is the way in which I can improve or assess the goodness of fit of the model. So these are the various aspects that I am looking at rather than the mathematics behind the building of each of these models. So we'll also talk about the conditional inference classification tree. We can very well discuss what are the key differences that are there in between each of these approaches while they are doing the classification of the data. We will also bring in the evolutionary classification tree and probably something that is different from the rest, which is the oblique classification tree. So we will talk about each of these things and we'll try to execute each of these algorithms in R to one single data set itself, so that we can see for this particular data set which model is more and more comfortable, more and more accurate. Now, the data set. Regarding the data set, I have to talk about some important things. So this data set is about the win, loss and tie. These are my response variables. So this is about one day international cricket. The data set that I have taken is about one day international cricket, which is a 50 over game. So the recent games that have been played by India against different oppositions, the recent games which have been played by India against different oppositions, the result of each of these games. So the result could be either a win or a loss or a tie. So I am considering the result associated with each of the games, and along with that I am looking at what is the role of one specific player, right? So in each of these games I am considering one specific player who is Virat Kohli, whatever the games he had played. So that is my sample size. So I am considering what is his contribution towards the win, loss or tie. Is he really influencing India winning, losing or tying a specific game? Is there any kind of pointers I can draw by linking from the historical data whatever the games that India has won or lost or tied? Can I link them to the performance of this one single player who is called as one day international sensation in the world of cricket? Is he really contributing? Can I say that a decision tree can be built based on his performance in that particular game? Can I try to predict whether India would win or lose or tie based on the performance of Virat Kohli in that particular match? So that is what is the intention behind doing this entire exercise, right? So that is the data set that I have taken. Let me look at this data set. It is there in this location india.csv. I am loading this data set, and just for a quick understanding, let me show you what is the size of this data set. So I am saying dim India, which is telling me there are 166 rows of data. Probably this is associated with the 166 games that Virat Kohli had played till date, since he would be continuing to play in the future as well. I want to build a model in such a way that I can assess to what extent India can win based on the performance of Virat Kohli. What could be the accuracy of my estimate? Right, so this is what it is. So there are 11 different variables altogether. Let me look at the structure of India, which is telling me, so this is what is the result. That would be my response variable. So there are three levels here: lost, tied and win, won. And if you look at the remaining things, score. Okay, what was the score that India has put up in that particular match? So innings, is it the first innings or the second innings? So did India bat first? If India had batted first in that match, it's the first innings. Otherwise, it's the second. Who is the opposition? There are 12 different oppositions that we are considering out here: Australia, Bangladesh and so on. Then we are looking at the venues. The venue is being classified as away and home, only two different levels. So is the game played in India or away from India? Then the runs. So how many runs did Virat Kohli score in that particular match? So what is the number of runs that Virat Kohli has scored in that particular match? Then we are talking about proportion. So what is the proportion of that total runs? So if I say Virat Kohli has scored 12 runs in this match and the total Indian score is 146, this is where I say proportion is 12 by 146, which happens to be 0.0822. So I'm looking at the proportion of runs that he has scored. So to what extent, how much proportion his scores could play an important role in the country winning the game. Then status, whether he was out in that game or he was not out. So it's a factor with two levels. What was the strike rate for Virat Kohli in that particular match? Did he score very briskly with a strike rate of above 100, which is number of runs divided by the number of balls faced? That is what we are calling as the strike rate. So if he has scored 60 runs facing 100 balls, then the strike rate is 60%. So that is what is being represented here: 54.5, 65.8, 81.8 and so on. So is the pace at which he has scored the runs really impacted the winning or the losing for a particular country, for India? So we are going to look at that aspect as well. And at the same time, at what position did he come to bat? So he has batted at position 1, position 2, position 3. So there are different positions at which he has batted. So the place at which he bats, does it make any kind of a difference in the way the team wins or loses? And what is the score at which he has entered the crease? So if it is 0 means he has come as the first or the second player, whereas after 1 or 2 get out, if he has come in the 3rd, 4th, 5th position, then it means after a couple of people are out, he has come to the crease to play. So in that case, I'm looking at what score he has entered the crease, so that I can assess whether his win or whether the country's win or loss is based on at what score he has typically entered the crease. So these are some of the influential variables I want to look at. So whether the country is winning, what is the chance of the country winning a particular game based on the runs that Virat Kohli scores, based on the opposition, right, and based on the score that India has to put up, and the result, the venue, is it home or away? And we are talking about whether Virat Kohli should be out or not out in that particular game, at what position he comes to bat, what is the strike rate at which he scores, and what is the score at which he comes to the crease. So these are some of the things based on which I want to build different kinds of decision trees for predicting whether the country will win the game or lose the game, etc. So the first of this classification tree that I am building here is a preliminary classification tree. And this preliminary classification tree is built with a package tree, and the function that we are using is also a tree function. So let me first install that particular package called tree. Let me install this package tree. Okay, so the package tree is successfully installed. So we'll use the function within that called tree function, where I will take Z. Z is the data frame of classes. So I'll be taking the Z typically in this function. If I have to take the Z, it's a data frame that is containing the class. So I'll be taking the result column from this particular data frame. So I'll take the result column as Z. Dot means I'm considering all others as my explanatory variables. So all the remaining 10 variables, I would be considering them as my explanatory variables. Then the data. The data is containing the remaining, what is the total data that we have considered for building the model. So here I will talk about splitting the data into a training data set versus a testing data set. So, but for the time being, let's consider whatever is the data, training data, that is what I have to provide as in the data section. And split. Split is a kind of logic, right? So let me try showcasing you this function called tree. Let's try what this function called tree gives me. Okay, no documentation because I did not load this package. I have only installed it. So let me load this package as well. I have loaded this package using library. After installation, every package needs to be loaded. So now let me see question mark tree. So you could see the documentation. A tree is grown by binary recursive partitioning. So it uses a mechanism called, right, the help is very useful kind. It uses binary recursive partitioning. That's a kind of procedure that the tree uses, right? Using the response in the specified formula. So I am giving a formula. The formula I am giving is the response variable tilde all the explanatory variables. So that is what I am giving. Choosing the splits from the terms on the right hand side. So based on these 10 variables, the splittings are typically taken care of. So input wise, first thing I have to give the formula, right? So from this I have to give the formula, which is the left hand side should be either a numerical vector. Yes, I'll give a numerical vector if it is a regression model, when a regression tree will be fitted, or a factor when a classification tree is produced. Now in this case, we are doing a classification tree. So the Z for me should be a factor variable. We have already tested that Z is factor variable with 3 different states: lost, tied and won. So these are the 3 states associated with that particular variable. And the right hand side should be a series of numeric or factor variables separated by plus. So if I am giving a 4 or 5 out of the 10, then each one I will separate it with a plus. No interaction term. No interaction terms means I can't give a colon, which is a kind of a multiplication between the 2 variables, or I cannot use a star. I can only use a plus between them, saying they are all independent of each other. And dot is allowed. Dot is allowed means you can take all the variables as your explanatory variable. Then the data is a data frame in which preferentially interpret formula, weights and subsets. So the whole data is what I am considering, and generally we will be using the training data for this purpose. If I have weights, I will go with them. All these are optional stuff. You can read through them, right? Control. We'll talk about this control slightly later. I've taken it in some other example. I can set a control in terms of what should be the maximum depth of the tree. Should it be 2 layers, 3 layers? So that is what you will be mentioning as a part of this tree dot control. Here I will not use it. I'll use it in some other algorithm out of these 5 which we are discussing. But look at some of the optional stuff. Method. It uses recursive partitioning. The only other useful value is model.frame. Either I can use recursive.partition or model.frame. Recursive.partition is the default one, so I don't need to specify any of them. But in split, there are 2 splitting criteria. right? This is again the mathematics behind the splitting. If you want, you can very well Google out what is meant by deviance based splitting and what is meant by Gini based splitting. But we can very well use one of these two splitting criteria, either deviance or Gini, and that's it. So we can give that as an input to the tree, and the tree is typically built, right? So let's see how the tree gets built with our data. So for that, first I have already loaded the data, right? Let's look at the steps now. So the steps are: first load the tree package, which we have already done. Get the data in the needed format. We have already got it as a data frame. One variable is representing the classes, which we have already got that part. We have the result variable, which is representing the three classes, won, lost and tied. Perform the preliminary inspection of the data. Take a summary just to see if there are some kind of NAs or some such kind of thing, missing values, etc., that are present in the data. So I'll take summary of India. So the score is minimum of 102, maximum of 418, and it's a numeric variable. Innings minimum of 1, maximum of 2. Result is a categorical variable. There are 64 lost, 98 won, but tied is 4. So probably it may so happen that I may not get a better result for predicting the tide. But yes, just because we wanted more than 2 categories, I have considered this. But otherwise, the result with respect to tide may not be a satisfactory result. So probably we may interpret only the goodness of it with respect to lost and won. So these are the different oppositions: Sri Lanka 39, England 22, so on. Venues wise, there are 101 away venues and 65 home venues. Runs wise, there is a minimum of 0 and a maximum of 183 that has been scored. Proportion wise, there are cases where he did not score any proportion of the total runs, and on the maximum side it has gone to up to 61% of the total runs has been scored only by Virat Kohli. 24 times he was not out, 142 times he was out. Strike rates ranging from 0 to 209. Positions range from the first position to 7th position, and entry scores were anywhere ranging between 0 and 376. So these are the situations. So I'm looking at the summary of each of these, and I don't see any NAs in any of the columns. So my data is good enough. Now the next part for me is split the data into randomly selected training data, which will be used to build the tree, and testing data, which would be used to test the tree. So this whole data, I will split it into a training data and a testing data, right? So for that, first randomly I have to split, but if it has to be random, it's better that I maintain the consistency of this randomness across all the 5 algorithms or the models that I would be using, rather than using 5 different random sets for all these 5 different algorithms. I want to use the same 5 set, same random set for training as well as for testing for all the 5 different algorithms. And that kind of a consistency can be achieved by setting a seed value, so that the same set of random numbers will be generated every time. So I'll set a seed value, set.seed. Let's say let me set a number 1000. Doesn't matter, any number you can put, any integer value you can put as a seed. So I'm setting the seed value as 1000. Now I have to split the whole data into training data and testing data. Generally 70% of the total observations I'll take it as a training data, and the remaining 30% of the observations approximately will consider them as a testing data. So to know how many total observations are there, I will consider n, which is talking about n row of India, which will give me the number of rows for India, which is telling me n is 166. So if I look at n into 0.7, which is 70%, it says around 116. So let me take 116 as my training data and the remaining 50. So my training data is 116 matches, and the remaining 50 will be used as my testing data, right? And I'll break the data into training and testing. The way we will create that is I'll create a variable called train, which will allow me to randomly select some 116 numbers out of the numbers between 1 to 166, which we will accomplish using the sample function, where I am setting 1 to n. So between this 1 to n, within this 1 to n, so there are 1, 2, 3, 4, 166 chits are there. I have to pick up 116 of them randomly. Out of these 166 numbers, I have to pick up 116 numbers randomly, and I will set replace equal to false, which means these 116 are picked without any kind of repetition. So they are picked without any kind of a repetition. So I am setting replace equal to false. So if you look at what is there as a part of the train, it is this: there are 116 numbers between 1 to 166 in such a way that no value is typically repeated. So this is my training data. These rows will represent my training data, and the remaining rows will be my testing data. So probably if you want, I can also put train data, which is nothing but I will be taking India. I'll take a subset of India, wherein I will choose only these rows which are there as a part of the train, but I'll choose all the columns. So that is what will be my train data. Whereas my test data will be again a subset of India, but the rows will be minus train. So whichever are not there as a part of the train will be the rows as a part of my test data. I will consider all the columns. So I have broken my data into train data as well as the test data. So this is what is the step. Split the data into randomly selected training data, which will be used to build the tree, and testing data, which will be used to test the tree. Now we can directly go ahead building the decision tree using the training data of 116 elements. So the most important part there is either I can use deviance as the splitting criteria, or I can use Gini coefficient as the splitting criteria. What I suggest is we'll build two models, one with deviance, one with Gini coefficient as the splitting criteria. Here few things I have to ensure: my response variable needs to be a factor variable, and if it is not, better convert it into a factor. In this case, obviously it's a factor variable, so I don't need to bother much about it. So let me start my fitting process. So I will say fit underscore tree underscore deviance. I'm using the preliminary tree, so that's where I'm calling fit underscore tree underscore deviance is what I'm using. I'm using the function called tree, wherein my dependent variable or the or the response variable is the result, and tilde dot means I'm considering all others as the explanatory variables. The data I'm taking as train data because I have already created a train data out here. So that train data would be used, and the split, in this case I'm using the split as deviance. So this is the fit tree that I'm building using the deviance as the splitting criteria. And let me build one more model. So we will compare these. So I'll say fit tree underscore Gini, right, where I would be using the split as Gini. That's the only difference between the two. So I'll go ahead and get into the fitting process, right? And I really want to see the response variable, is it a factor or not? Obviously it's a factor, which we already know, but otherwise if I really want to check whether it's a factor or not, use the attributes function, say train data dollar result. You can just see what is it's a factor containing three levels: lost, tied and won, right? So that is what is it. Now I can look at the details of the fitted tree. I can give the name of the model. So I'll say fit tree deviance, where I'll get the details of the fitted tree. Now this is the tree all about. I could see that initially the runs less than 21.5 is the criteria, and otherwise it is runs greater than 21.5. So that's the way the splitting has been done. Runs less than 21.5 versus runs greater than 21.5. So Virat Kohli is scoring less than 21 runs versus he is scoring more than 21 runs, right? 22 and above. That has been one of the prime criteria that has been used for splitting. And you could see that if he scores less than 21 runs, the result is coming out like lost. There is a 60% chance. Now if you try to interpret this output, you could see here, this is the node number 2, split. The splitting criteria is runs less than 21.5, so he is scoring 21 or below. And there are 43 such instances where he scored 21 and below. Out of this whole training data set, there are 43 instances where he has scored 21 or below. The deviance in this process, so because we have used the deviance as a mechanism, the deviance is 76.26. The y value, which is my response variable, the response variable is lost, and we are given the probabilities. There is a 60% chance that India will lose. There is a 9% chance that there could be a tie, and a 30% chance of a win. Similarly, if he has scored more than 21.5 runs, that runs is the first splitting criteria, less than 21.5, greater than 21.5. There are 73 instances where he has scored more than 21.5. The deviance is 83.71. The result is 1. Wherein you could see that there is a 26% chance that the country will lose, whereas 74% chance that the country will win. So now, after the first split, here the deviance is coming out to 76.26. Here the deviance has come to 83.71. Now there will be a further bifurcation of the tree to see whether the deviance can anywhere be reduced. So this is where the two other things, one more split came out saying the score is less than 301. Right? If the team scores less than 301 versus the score is more than 301. Right? If he has scored less than 21, but if the team score is less than 301, where there are 37 instances out of this 43. Out of this 43, where he has scored less than 21, the team score was less than 301 in almost 37 cases. Deviance came down to 55.46. Result is loss. There is a 70% chance that the team will lose. Only 24% chance that they can win. But on the other side, if the team score is more than 301, which there are 6 instances out of this 43, deviance is just 7.6. The result is 1. Either they will tie the match or they will win the match. So if they score more than 301, even if Virat Kohli scores less than 21, they will definitely win the game. And similarly, still they want to reduce So now here there is no further bifurcation because the deviance came to 7.6 and it can't be split any more further. So there is no indentation below this 5. Whereas below this 4, I could see again a split, opposition. Australia, England, South Africa, Sri Lanka. Right? When the score is less than 301, there is a further breakup wherein they are looking at countries Australia, England, South Africa and Sri Lanka versus Bangladesh, Netherlands, New Zealand, Pakistan, West Indies and Zimbabwe. Here there are 21 such instances where the deviance came down to 21. The team has lost. 85% chance if the opponent is Australia or England or any one of them. 85% chance that they will lose the game. Only 5% chance, 4.7% chance that they can win the game. But similarly, if the opposition is any of these, there is a 50% chance that they will lose the game, 50% chance that they will win the game. So like that, the whole split is typically being created based on the data. Right? We got a clear cut split in this case. Similarly, I want to look at the other model to see which ones are better. There is nothing called this is good, this is bad. We have to explore all the models. So here the rule is slightly different. When I am going with Gini, you could see the rule is slightly different. The first parameter that came out is innings. Innings less than 1.5, which means the game is played, India batted first, versus innings greater than 105, which is it's the second innings. The deviance here is 84, the deviance here is 99. If first of all it's the first innings, there is a 50% chance that the country is winning. Only a 45% chance that they are losing. Forget about the performance of Virat Kohli here. Whereas if it is in the second innings, there is a 63% chance that the country has won, it will be winning. So if India bats second, there is a high probability that they are going to win. Then within this, if now again this deviance has to be reduced, then Virat Kohli batting at positions less than 3.5, which means 1, 2, 3. So where there are 38 such instances in the first innings and 52% chance that the country has won. Whereas when he has batted beyond 3.5 positions, 4, 5, 6, 7, this is the deviance and there is a 46% chance that the country has won, will win, 38% chance that it will lose and 15% chance that the game could be tied. And within that, again, if he has batted in the fourth or much above fourth, if he has batted in the fourth, there is a big chance that the country has lost the game. In the first innings, if he has batted in the fourth position, there is a 50% chance of a loss. But if he has batted in the fifth, sixth, seventh positions, there is a 60% chance of a win. So that's how you could typically take the whole thing forward. And this is how the Gini coefficient based tree has been built. And this is how the deviance based decision tree has been built. So I'm getting the details of the tree by looking at this entire stuff. Then, so the items displayed, we are getting the branch numbers, right? These are the node numbers. The splitting criteria that is being used, runs greater than something, runs less than something, that's the splitting criteria. Number of samples that are going along the split, 51 observations, 38 observations and so on. The deviance that is associated with the split in each of the cases, the intention is to reduce the deviance overall. The predicted class, whether India is going to win or lose or whatever. The probabilities of each of the classes, what is the probability that the country will win, the country will lose, the game gets tied. And stars are the terminal node. So this is one terminal node. So how do I interpret this? If I have to interpret this, okay, if India plays in the first innings and Virat Kohli plays in the top 3 positions but scores less than 13 runs, against Australia or England or New Zealand or Pakistan, the country has won. There is a 50% chance of winning and 50% chance of losing. Whereas if the opposition is any one of these, Sri Lanka or West Indies or Zimbabwe, there is a good chance that the country has lost. India batting worst, Virat Kohli playing in the top three, and the oppositions are Sri Lanka, West Indies or Zimbabwe. There is a big chance that India will lose the game. So that's how each of the tail nodes, terminal nodes need to be interpreted. Probably one more interpretation I'll give. Let's say this is a terminal node, right? So India batting in the first innings, or probably let me look at this from here, right? Now, India playing in the second innings greater than 1.5. Virat Kohli batting in the top three positions. But if his strike rate is less than 67.84 and he scores less than 4 runs, then the game has been lost. 66% chance that the game will be lost, only 33% chance that the game will be won. But if his strike rate is greater than 67.84 and the oppositions are Australia, New Zealand and South Africa, there is a 58% chance that the country will win. And if he is entering at less than 35 runs, the game has lost, which means the opening partnership should be more than 35. And if he has entered after the opening partnership of 35, almost he has got all the games won. So you could see by simple logic, I can very well explain this whole tree. So that is what is going into the understanding of this tree. Then, if the tree comes out in minimum with the minimum deviance is the first node itself, then there is no way I can build the model. It's a random. There is no way any of these things are influencing the win or a loss. But here, because we got the tree, some branches, I can very well rely on the output that is being given by the tree. I can also look at the summary of the model. So I'll look at the summary of both the models first thing. So let me take the model fit tree deviance model. Let me look at the summary of this. Few important points for me here to look at. The number of terminal nodes are 15. So there are 15 different rules. Right? I'll look at the summary. There are 15 different terminal nodes out here. Then variables actually used in the construction of the tree 1, 2, 3, 4, 5, 6, 7. Though I have given 10 variables, only 7 of them are important, 3 of them are completely ignored by the model. Residual mean deviance. We are talking about on an average the deviance that is existing is to the extent of 70.18. I have to reduce the deviance. Any other model which can reduce, it can result in much more reduction of the deviance. 70.18 divided by 101. That's the total deviance, which is working out to 0.6948. So on an average, the deviance is 0.6948. I have to look at, when I have to choose some other model, it has to be the case that that model should have a much lesser deviance compared to this model. And the misclassification error rate, the wrong classification is 15 out of 116. So 15 of them are wrongly classified out of this 116. This is with respect to training data, right? I have to do it on the testing data, but when we are looking at training data, the misclassification rate is 12.93%. So that much of error is there with the model that we are creating. So that's what we could look at when we are doing the summary of the model, right? So the most important things to look at are the residual mean deviance, which is to the extent of this much. Misclassification error rate is to the extent of 12.93. But if I am using fit tree Gini for the same purpose, now in this case, again the same 7 variables are being used. Is it the same 7? Runs is considered, score is considered, opposition is considered, proportion is not considered here, right? It looks like proportion is not considered, but the position at which he came to bat is considered. Entry score is considered. Here venue is considered, whereas here the venue is not considered, but innings are considered. Strike rate is considered in both of them. So both of them are using a completely different technique to build. So there are 17 terminal nodes here. When I am using the Gini as a base, there are 17 terminal nodes that came up. The residual mean deviation is much higher in this case, 1.032, much higher compared to the deviance model. And even the misclassification rate is 27 out of 116, resulting in 0.2328, which is 23.28% is the kind of misclassification. So when I'm looking at with respect to the training data, Gini is looking not that appropriate compared to that of a deviance. But let's do a graphical plot of both of them. So I will do the plotting of the same thing which is there in the tree part. I will get it in a graphical diagram part. So I am taking both the plot as well as the text associated with it. So this is how the runs less than 21.5, score less than 301, oppositions, these oppositions, proportion less than 5%, right, score less than 206. So we are seeing this is the kind of a tree that can be built with respect to the deviance. Whereas if I am looking at it with respect to Gini, the deviance, the tree is more like this. With respect to Gini, if I am taking, this is the tree. Innings less than 1.5, less than 3.5 position, runs 13 and so on. Now, so that's how the plotting of the tree and the text which talks about the rules associated with each of the tree can very well be looked at, right? So when we look at the plot, one important point that we have to look at is the height of the vertical line. Now here the vertical line is very small. So it means that the deviation has come down just marginally. But here you could see the height of the vertical line is much higher. So which means the deviation has come down drastically. Here the deviation has come down drastically. Here also the deviation has come down drastically. So wherever you see that the height is much bigger, this means that the deviation has come quite drastically. And when the vertical line height is much lesser, then it means that the deviation did not come down that heavily. So the longer the line, you could see here, the longer the line, the larger is the reduction in the deviation. Now, there is a possibility, as we have discussed earlier also, with the classification trees, there is a possibility of overfitting. So for that, I want to do an assessment of the model, right? We will get into the one thing is I will try to test it on the testing data. That's one aspect. But before that itself, when we are doing the assessment with respect to the overfitting of the model, we use the mechanism of cross-validation. We have already discussed this cross-validation, right? We will split the whole training data into small groups, and for each of the group, so this would become the test data in the first attempt. All this would be taken as a part of the training data. After that, this process will be repeated by taking this as the testing data, the remaining as the training data. So like that, the process will continue. So if I am talking about some set of groups, so I have to specify how many should be there as a part of the testing data. So here we have 166 altogether, and I want 50 of them to be there as a part of the testing data. So 116 should be there as a part of the training data. Now what will happen is different combinations of 50 are going to be a part of the testing data, and the remaining 116 would be a part of the training data, right? So that is what we are calling as the holdout sample. We are holding out 50 observations. For each holdout sample, fit the model, note at what level the tree gives the best result, and after that change a different holdout sample and keep repeating the process. I want the best possible result in each of the holdout. So whichever the holdout is giving me the best possible result, I'm going to consider that particular step. So here we would be using a function called cv.tree. cv.tree is actually taking care of handling the cross validation part. So let's see what it is. If I look at this cv.tree, runs a k-fold cross validation, right? K-fold cross validation means the k elements would be there as a part of the testing data to find the deviance or number of misclassifications. So I can use it either with a Gini or with respect to the misclassification, which is the Gini part, or I can use the deviance, whichever of the ones. So it runs a k-fold cross-validation experiment to find the deviance or the number of misclassifications as a function of the cost complexity parameter k. So one, I have to give the object. The object is the tree object. So my fitted model is what I have to give as an input to it. Then rand, which is talking about an integer vector of length, the number of cases used to create the object, assigning the cases to different groups for cross validation. If I want to give, I can give some kind of a random number, but mostly important, the function to do the pruning. So we have two different kinds of functions here. The functions to do the pruning, we have two different functions. Either I say prune.tree or I can say prune.misclass. So we have two different functions to talk of here. One is prune.tree, one is prune.misclass. So I can use any one of these or both of these to try to see this. A number of folds of the cross validation, which is very important, I'll set it to 50. So this is how I will use my cross validation part. So again we can create two of them. Fit tree deviance. I'll give one more saying misclass. Right, I'll take it as fit tree deviance underscore misclass, where I'm using the cv.tree function. One of the input to that cv.tree, the first input is the object, which is the fit tree deviance. The k I will set it as 50, and I would also look at the function in this case as prune.misclass. This is one that I am doing. Similarly, I could take it as, instead of misclassification, I would also consider the prune.tree. The same fit.deviance. Instead of saying prune.misclassification, I'll say the function as prune.tree. Now the same way, I would maintain two of them. One for Gini, the same pieces I will maintain even for Gini. I'll say underscore misclass, wherein I will use cv.tree. Here The model that I am using is fit underscore tree Gini. K I will set it as 50, and the function will be function prune dot misclass. This is one, and similarly the same thing I can give for prune dot tree. So I am looking at 4 of them. Here I will use prune dot tree. Right? So this is what we are looking at, the misclassification understanding. So these 4 I will try to plot to see, right, where the error is typically coming up. Right? The misclassification, how many are getting misclassified for each of the scenarios, depending on the size that I have taken, how many of them are typically getting misclassified. So the size of the tree, okay, let me try going ahead with it. So let me take the plotting in a 2 by 2 kind of stuff. So that's where let me set par mf row equal to c of 2 comma 2, so that I'll get a 4 by 4 tree out there. So let me use this 2 by 2 kind of a tree. Within this, first thing I'll plot. First, let me plot all these 4. I'm going to plot. So the first one I'll plot is the fit tree deviance misclass. So it's looking like the minimum deviance has come out, right, when we are talking about a size of 4. The minimum deviance is coming out here. The misclassification rate is much lesser out here, right? Whereas if I'm looking at the other one, fit dot deviance fit tree deviance tree, oh, the minimum deviance again is coming out when the size is around 2 or 3 instead of 12 and 14. Right, the class verification result is telling me that it's better to prune the tree, right, instead of going towards the size of the tree of 14 or something. It's better to prune the tree at 4. It's better to prune the tree at 2 or 3 levels, right? So this is what is the misclassification telling me, whether I should go till that long, or it's better that I prune the tree at the size of 2 or size of 3 kind of stuff. Similarly, if I try plotting the Gini part, right, I try plotting the Gini part, I could see that the misclassification again is with a size of 5 or something. Right, as the size is increasing, again the misclassification rate has gone up. And similarly with respect to tree also, I could see that the misclassification rate is much lower at very small sizes. So I could really think of pruning the tree. So this is a kind of an input for me to go ahead in terms of pruning the tree. And the pruning of the tree, I can very well go ahead, but if you look at the tree algorithm, the control, a list returned by tree dot control. So I have to set something as a part of tree dot control. So let's see what is there as a part of tree dot control. So these are some of the things that I have to give as a part of tree dot control. Either I can give number of observations in the training set. Minimum cut is 5, which means the minimum number of observations to include in either of the child node. So I can set some such kind of a minimum cut kind of a restriction, or I can set minimum size equal to 10, which means the smallest allowed node size. So the number of nodes, what is the minimum size of the node? and minimum deviance is 0.01. So some of the things I can very well specify something like this. So probably here tree dot control I can set minimum cut equal to 5 or minimum size at the smallest allowed node size. The default is 10. So either I can set a minimum size there or probably I can set minimum cut. So let's see if I can improve the model anywhere. So let's try the fit dot. One of them let's try. Right, I want to try one of them. Okay, fit dot tree Gini we will try. Wherein one more attribute that I am going to bring is control. Control is equal to tree dot control of, I have to specify the arguments within which I am specifying min cut, right? Minimum I want to put a cut of 10 observations at least in each group. So, and number of observations also I have to give, right? There is no default for the number of observations. Number of observations in the training set I'll have to give NOBS equal to 116. So this is what is the new tree. Now you could see the fit tree Gini now, the updated one. You see it's a very small size tree. Minimum of 10 observations are there in each of the nodes, right? So this is what is a much better tree compared to the earlier one. Similarly, when I go with fit dot right, this will reduce the overfitting of the tree. So instead of here, let me go with deviance, and here also let me go with deviance. So this is what would be a much better tree. For the deviance also, the size of the tree now has come down drastically. So this is what is the tree: runs less than 21.5, runs greater than 21. Oppositions are this: score grade less than 279, 279.5 greater. Oppositions. Right, so this is how the whole scenario can be built with respect to the deviance model and with respect to the Gini. So this looks like much more optimal. If required, again I can repeat the process, try to see how many nodes. Now if you see in the, here I require better 4 or 5 nodes. In the leaf node should be 4 or 5. Whereas in this case I am ending up with around 6 or 7 leaf nodes. So with 6 or 7 leaf nodes, again the error rate is somewhere here. Right, it's better that I reduce it even more further. So let's say instead of min cut of 10, probably I want to set a min cut of 20. Then let's see what is coming out. If I'm setting a min cut of 20, I am getting, yes, only my leaf nodes are 1, 2, 3, 4, 5. Only 5 leaf nodes, then in that case probably the deviance is looking much lesser. The focus is only on runs, entry score and the opposition, only that much. So this would be a much better model compared to the earlier model, going with the min classification or the Gini kind of the misclassification rate or the Gini. The same scenario I can, so this is something you can play around with it, right? The same scenario you can play around, see using this cross validation mechanism, what is that size of the tree where you could typically find the least possible misclassification rate or the least possible deviance in each of the models, and based on that you are going to choose the size of the tree. Based on that, you want to choose the control part associated with the tree, right? So that is what we are providing as the input out here. All right. So now let's go back. So we have understood the misclassification part, and how do I really go ahead in terms of pruning the tree using the tree controls. So if the minimum comes closer to the number of branches in the original fitted tree, then there is no need to prune. But in my graph, the minimum is not coming with the number of branches that are fitted. The minimum is coming at 4 here, probably at 2 or 3 here, at 5 here, at 5 here. So that should be the number of nodes that should be there as a part of the tree to make the tree more and more appropriate. So that's the reason I have to prune the tree in this case. But if the minimum comes out towards the last, right, if the graph comes out more like this, so the minimum is coming again towards the number of the size which is of the original fitted tree. In that case, I really don't need to prune the tree, but in this case, I am supposed to prune the tree. Okay, so now the pruning is done. I'll be using the fit tree deviance and fit tree Gini accordingly. Now, I have to go ahead in terms of prediction. So we'll do the prediction on the tested data. So that's where let me use pred underscore deviance is the model let me use, because we are doing the prediction with respect to the deviance. We'll use the function called predict, where I have to use the model. So I'll use the fit tree deviance model for this, right? I'll use the fit tree deviance model, and the new data for me for which I am testing is my test data. So this is the input that I have to give, and the type I have to give it as class, which will give me what is the class that is associated, whether this should become win or lost or died as per this model. So that is what is coming out with pred deviance. Now the same way I can go with pred Gini. I'll go with pred Gini. So the model that I'm using is fit tree Gini. The new data is test data, type is class. So we are trying to test out both of them. So if you look at pred underscore deviance, for the 50 of them it has given, this would be the result. 1, 1, last, last, last. And similarly when I go with pred underscore Gini also, I'm getting the result for all those 50. 1, 1, 1, it looks like very few of them are lost. Majority of them are looking like 1 when I'm going with the Gini model, but when I'm going with this model, I see a good combination of 1 as well as lost. So now I can go with a table just to understand the overall process, right? 1, I'll take it as the test data, which is the actuals. So from that test data, I will take the result column, that is the actuals, and I will take pred underscore deviance, which is the predicted part. So both of them I'm plotting, and their names DNN I can set them as two different. For the first one I will set it as actual data, and for the second one I'll set it as predicted, right? So this is what I want to create as a table: observed versus the actuals versus the predicted. So this is what is the story in case of Gini, in case of deviance. The same table I can create with respect to Gini as well. So I'll take pred underscore Gini. So in this case, this is what is the actual versus the error. Now I could see here, how do I interpret it? So there are, so if you see, totally there are 19 matches where the team has lost, but out of those 19, 11 of them are predicted correctly, whereas my deviance model predicted in 8 of the cases that the country will win. but they haven't. The same logic here, there are 31 matches in which the country has won, but the model has predicted in 16 cases correctly out of that 31 that the country is going to win, and they have really won. Whereas in 15 cases, the model has predicted that the country will lose, whereas they have actually won. So, if I have to look at the accuracy, it is on the diagonal. 16 plus 11, 27 out of 50 are accurate. So, going with this particular model, going with my deviance based model, the accuracy is around 54%. Whereas if I'm going with Gini based model, 2 plus 23, 25 out of 50 are accurate, which is a 50% accuracy. So between these two models, if I have to go with, it looks like the first one is more appropriate. But more than that, I can also look at few other parameters like log likelihood. Right, I will look at the log likelihood associated with the deviance tree. Okay, for these models, I think I cannot find that out. Even the AIC, I'm not sure. So with the tree, because these are more of statistical measures. Oh, sorry. So not applicable. Let me see log likelihood. No. So you cannot apply this for a tree class, fair enough. So here we can use this kind of a testing data to really assess the accuracy of the model. The error rate in this case is 46%, the error rate in this case is almost 50%. So at this point we can say that we are able to do the prediction of how much Virat Kohli is contributing to the success of Team India. In almost 50% of the cases our estimates are correct, 50 to 55% of the cases our estimates are correct, but in the remaining set of cases we are losing out. So we really need to see, is there any better kind of a model, right? This is what we call as a confusion matrix, right? I hope you know by now. This is a confusion matrix. We are seeing across the diagonal they represent the correct predictions versus the actuals, whereas anything away from the diagonal they are more and more of wrong predictions of the data. So we are calculating the error rate of the fitted tree in both the cases, in which case we have got around 50% as the accuracy of the model depending on the performance of Virat Kohli in that specific match. Alright, now we will try to use the same set of data, same objective on a different models. We said we will use 5 different models, right? So we'll use the same mechanism on different models to really see if any of those models are able to improvise, our prediction accuracy, so that we can very well predict whether the country is going to win or not based on the performance of Virat Kohli in that particular match. Alright, so let's move on to the next set of models. Now, the next model that I want to look at here is a C5.0 classification tree. It is based on the concept of entropy. Right there we have looked at the tree primarily based on either the Gini coefficient or the deviance calculation, and based on that the splitting of the tree has been performed. Here it is based on the measure of entropy, which talks about the measure of disorder in the sample, to what extent the observations in the sample are pure, and to what extent the observations in a particular split they are mixed. What is the proportion that the observations are pure in a particular split versus what is the chance that they are mixed in a particular split. So there is a concept of entropy, there is a formula for it, right? And you can very well check out for all those things. And by doing a split, what is the extent to which the entropy has come down, which is what is called as information gain. So initially the entropy is computed without the split, and based on one particular split, let's say based on the runs, I'm doing a split. After doing the split, to what extent the entropy has actually come down. The extent to which entropy has come down is an indication of information gain. Means because of by being able to bifurcate the data based on the runs, I am able to reduce the error part. Probably you can think of entropy as a kind of a measure of error. So the error, just like a deviance, the error got reduced, which means this information that we have got based on the explanatory variable is a much better information for doing the classification of the data. So for each attribute, we are going to look at what is the level of reduction in the entropy, what is the level of increase in the information gain by doing the split based on that particular attribute. So what is the expected reduction in the entropy by partitioning the data set on a given attribute? If there is a big reduction in the entropy, it means that that particular variable is contributing very heavily towards the classification. But if the entropy does not come down at all, which means that particular variable can very well be ignored for doing the classification of the data. So that's how the entropy, reduction in the entropy, which is otherwise an information gain, they can very well be looked at in terms of assessing the goodness of the classification tree. And the best attributes for partitioning the data set are chosen. So we have 10 different attributes in our model. So probably not necessary that all 10 needs to be used. Even our earlier tree algorithm, even when we have fitted the full tree, it has used only around 7 attributes, both in the deviance case as well as in the Gini case. So it's not necessary that all 10 of them need to be used, but whatever are used, it will use the best possible attributes which are used for partitioning the data set, and accordingly the decision tree is being built in case of C5.0. So we have a package called C50. Using that C50, we'll use a function called C5.0 for that purpose. So let's install this package. We'll install the package C50. Right, we have installed the package. Let me load the package also. I've loaded this package C50, right? But I have to use the function called C5.0. So let me try to see what is this C5.0 function all about. It fits classification tree models or rule-based models using Quinlan C5.0 algorithm. So that's the typical logic in terms of creating the tree. So we are seeing here either I give a data frame or a matrix of predictors along with a factor with 2 or more levels. So this is one kind of an implementation, but here I am looking at this kind of an implementation wherein I am looking at a formula. We'll give the formula just like the way we have given in case of the tree model. I have to give the data. We know what to give as a part of the data. Then that's it. These two I can give. If I require some kind of control, I can give the C5.0 control. I can very well set control equal to C5.0 control. Within this control, again, all these things I can give. So minimum number of cases I can set here. It will take 2 as default, right? So probably one or these 2 of them, if you really want to change, you can very well change them. By default, there is an early stopping. So the C5.0, the goodness of this model is You really don't need to prune the tree. There is an automatic pruning of the tree that is happening. Only when you don't want an automatic pruning of the tree, you have to specify it separately. So here only two inputs are sufficient for me. I can give the formula and the data. So let me take fit C, fit underscore C50. Right, so here there's no specific algorithm or something where, I mean, there are no specific criteria or options for me. So I'm setting only one kind of model out here, C 5.0, where the result, the remaining things are something which we have already taken care of. Right, here input wise, first I should give me the data frame of the class. So we have a result variable which is containing the classes. Data is the data set of attributes used to build the tree. We are using dot, which means all the other variables will be taken as the attributes to build the tree. And okay, some of the steps which we have already done because we are using the same data which we have used for building the actual tree model also. We have loaded the C50 package, got the data, preliminary inspection is done. We have split the data into training data and the testing data. So the same data set is what we are going to use for C 5.0 also. So now I am building the decision tree using the training sample. So that is what is my next step. So C 5.0 result tilde dot, and I am setting data is train data because we are using only the training data part here. Alright. So the model has been fitted. Some of the common things that we can always do with every model that we are getting. First, I can type in the name of the model to get some details about it. Fit C50. Some details for me regarding the model. There are 116 samples, 10 predictors. The tree size is only 3. So it's a very small tree that we have got using the C 5.0 algorithm. In using the tree size has gone to 15, whereas here we are getting a tree size of only 3. So we can always type in the name of the tree like this, or in some cases I can do a summary of that tree. Right, some of the common things that we can always do. So you could see the summary of the tree. So there are 116 cases. This is how the tree got built. Score greater than 309. Irrespective of who has scored what, the country has won. Right? There are 15 times the country has won and 2 times it has lost. So the moment the score is 309, there is a high probability that the team is going to win. But only when the team score is less than or equal to 309, depends on whether Virat Kohli is scoring less than or equal to 21 or he has scored more than 21. If he is scoring less than or equal to 21, there is a lost. 38 of them are typically lost. Only in 12 cases the team has won, which means the score, there is a high chance that the team will lose the game. But when he scores above 21, there is a 63 victories versus 19 defeats. Right? Out of the 63, out of these 63 cases, only 19 of them are erroneously classified. Right? So overall you could see that there is a high chance of winning out here. So basically it's like there are 63 such cases and only 19 of them are misclassified. Here there are 15 such cases, only 2 of them are misclassified. Here there are 38 cases when he has scored less than 21, only 12 cases where there is a misclassification, which means the remaining 26 cases the team has actually lost. And if you look at the evaluation of the decision tree, the size is only 3 because only 2 parameters are being considered, one being the score overall score and how many runs did Virat Kohli typically score. The errors are 33 overall. Here there are 19 errors, 12 errors and 2 errors. So overall 33 and overall misclassification rate of 28.4%. And if you look at the misclassification part here, right, 26, if you are looking at the last, 26 of them are correctly classified, 19 of them are wrongly classified. Similarly, you could look at the tied category, right? Two of them are being classified as lost and two of them are being classified as won. And similarly, with respect to winning, 57 of them are being classified correctly, only 10 of them are being classified as wrong out here. So, the accuracy, if you look at the error part, it is this 19 plus 4 plus 10. 19 plus 4, 23 plus 10, 33 are misclassified. The ones on the diagonal, 26 plus 57. 26 plus 57, 83 out of 116 are correctly classified as per the training data. I have to test it out in the testing data. But importance wise, score is having a very high importance of 100% followed by runs, which is 87. All others runs scored by Virat Kohli. So definitely we can say that the runs scored by Virat Kohli are typically contributing to the decision regarding is India going to win based on the performance of Virat Kohli in that particular match. So I could also assess the importance of the variables using C5 imp, right? I can very well assess the importance of the variables, which will get it as a similar kind of result. Right, the result is nowhere different. Only the first two of them are 87 and 100, but all others are going to be 0, which means all others are not contributing much to the model. So use the validation data set and the fitted decision tree to do the prediction. Now I can very well do the prediction part. Pred underscore C50. I'm doing the prediction part. So we'll use the function predict the same way we have used earlier. So we'll use the model fit underscore C50. That's the name of the model. And the new data that we are using is the test data. And the type, again, we have to specify it as a class so that it will give me the output of which one belongs to which. So this is the pred C50 that we are getting. Again, I can use the same table function which we have used earlier also. So I can say test data dollar result. That's my actual result of the game. The pred underscore C50, which is the predicted result of the game. I can set the headings using the DNN. C of the actual. The first one is actuals and the second one is predicted. Right, so that's the table that we are getting. So in this case, at least this is looking slightly better. 8 and 21, that's the accuracy. So 29 out of 50 is the accuracy of the model. Almost 58% is coming out to be the accuracy of the model when I'm going with the C5.0 algorithm. So if you see right now, the tree algorithm that we have used, one with deviance and the other one with Gini, and now we have used C5.0 and we have tested it on the testing data. The deviance has given me the accuracy of 54%. Gini has given approximately 50%, whereas C5.0 has given me 58% in terms of accuracy. So I can very well say if these are the three options that are there in front of me, I want to use the C5.0 algorithm to typically assess the chances of the country winning based on the performance of Virat Kohli. So we have calculated the error rate of the fitted tree, and we can also estimate the probabilities of each of the classes. Okay, this is one more thing. So let me take in the predict C underscore C50, and I want to take the probability. What I really want to look at is, instead of setting this to class, let me set it to prop. And now if I want to print for all these 50 people, what is the probability that they belong to the last or tied or won? Okay, the 16th one, 69% chance that the team will win. So some of them could be on the borderline. Those cases we have to be slightly careful when we are doing the assessment, because there could be a chance of a tie as well. Right here, if we see, there is only a 5% chance of a tie, whereas here it's only 0.05% chance for a tie. So we have different kinds of cases cropping up based on the scores and runs as the criteria. So we have to see in which case the decision is more on the borderline versus in which cases the decision is very clear and apt. So that's one more way of doing the classification more and more appropriately using the C5.0 tree. So using these two methods, so up to here, this is what is the situation that we have landed up in. We have looked at the decision trees, seen to what extent the variable can be estimated, the classification variable can be estimated based on the various explanatory variables, which explanatory variables are playing an important role, in terms of determining the decision variable. In each of the algorithms, the variables are different, but overall I'm more interested in looking at what is the level of accuracy and the error rate when I'm applying this model on the testing data, right? Now here, just that the C50 algorithm has given me an accuracy of 58% does not necessarily mean that C50 is always better than the tree algorithm. In this case, for this kind of a data set, we are able to get better result with C50 algorithm, but it may not be the case for some other data set for some other objective, right? So we have to understand that there is no one single model, one single algorithm where which is universally better than the other algorithm in all cases for all kinds of data. That's one important point that we have to keep in mind. Now, moving on to the third important algorithm in this context of classification trees, wherein we are talking about the conditional inference classification tree. So it's also a kind of a non-parametric regression tree, but it is embedding the tree structured regression model. So the regression models are going to come up, but for each of the structures in the tree, right? So this is the typical interpretation of the conditional inference classification tree. But of course here I don't think we have done the plotting of this model. So let me do the plot of this model also. So this is how the plotting of C50 is going to come out. Score less than or equal to 309, greater than 309. Right, runs less than or equal to 21, greater than 21. And this is how the classification came. Here there is a good chance that the team can lose. Here there is a good chance that the team is going to win. And here also there is a good chance that the team is going to win, but definitely it's not going to lose when the score is greater than 309. Alright, so let me come back to this conditional inference classification tree. So it's also a decision tree, but it will give me much more information regarding the distribution of the classes in the terminal node. So whatever are the leaf nodes that are going to come up, a much more detailed information is going to be provided in the leaf nodes. We'll see what kind of information we are going to get there. So for this purpose, we would be using a package called party, and within that we'll use the function called C-tree. C-tree is nothing but conditional inference classification tree. So let's use that package. Right, will be install packages. I'm installing the package party. So all the required packages also would be installed accordingly. We would also load this package so that we'll try to understand. Okay, the prior installation of the party package cannot be removed. So there is some package that is already existing, and that party package is not getting removed. The best way for doing that is, let me close it. Right, so let me save this workspace. Right, let me save this workspace with the name India. Let me close R. Let me reopen it. So let me load the package again. I'm loading the workspace, which is India. Okay, we have loaded this. Install.packages party. Yeah, let me try again. Yeah, now I think this party package has been installed properly. So let me load this package, library package. Library party. Now let me load this package called party. Yes, now the party package is loaded properly. Sometimes when it does not get loaded, it's better to close the session and reopen a fresh session. But in the meanwhile, let me just check if the data is stored for me. So I'll take the head of India. Yes, the India data is saved, so I can very well use this. And probably if required, I'm also looking at my dim of train data, so that just to check that all of that is saved. Yes, 116 rows, 11 column. Okay, now I should talk about what is this C-tree function. Look at the C-tree function, conditional inference tree. Recursive partitioning for continuous, censored, ordered, nominal and multivariate response variables in a condition. So it can actually do the partitioning for all these kinds of data. Even if your response variable is a continuous variable, you can use this. Even if it is a censored variable, you can use it. Ordered variable, nominal. Now in this case, it's a nominal variable with 3 different categories, but you can still use it. The formula goes like this, the function goes like this. We are talking about a C tree with a formula, right? The data we are providing, subset, weights, we don't require control. Controls is something which you can set, especially if you want to control the size of the tree, right? So we can very well talk about C tree underscore control, and within the C tree underscore control, we can very well specify the different values associated with C tree underscore control. So you can very well specify the maximum depth of the tree, right? You could also, so there are a few important controls that you can specify here. The size of the tree is something that you can very well specify. Okay, so now you could see the C tree underscore control. You can very well set the test statistic, the type of it, whether it's a quadratic or maximization that you want to give, the testing type. You can give any of these different kinds of tests. You could very well specify the minimum split, right? The minimum split is the minimum sum of weights in a node in order to consider for splitting. Minimum number of buckets. So you could very well specify all these things. The minimum criteria, the maximum depth of the tree. So you could very well try all these kinds of stuff as a part of the control parameters that you are setting. So that's the thing as a part of this conditional inference tree. So let's do the plotting of that tree, right? Or let's do the fitting of that tree. So I'll call it as fit underscore C tree, and probably we'll have to set the depth. But let's see initially without the depth. Let me see if the fit underscore C tree, probably let me set it as underscore 2 or underscore 3, talking about the depth of the tree being 3, or probably let's set it as 2 initially. Right, I'm setting the fit tree wherein I'm using the C tree function. The result is the dependent variable tilde dot. The data for me is the train data, which is the training data in this case, and probably I can set the control because I'm setting the tree depth as 2. So I'll set train controls equal to C tree underscore control, wherein I'm setting the max depth equal to 2. Now probably all other things also I can very well set. Those are some of the optionals that are available for me. Right, in C tree.control, I can very well set the minimum size of each of the node and few other aspects as well. Here I am setting the size of the tree, the maximum depth of the tree to typically 2. At the max, it will be 2. And if it is 0, then probably no tree is typically fitted. So 1, we have fitted using 2. I can also try fitting using 3. Maximum depth as 3. But if I don't consider anything, then it is, I'll simply put it as C3, where let it determine what should be the depth. So I'm not controlling what should be the depth of the tree here. So it's like unlimited depth. So I'm just giving only this much as the input, wherein my intention is to look at the unlimited part of it. I'm not giving any kind of control in terms of the maximum depth of the tree. So these are the 3 trees that I'm looking at. Let me see the graphical. So first I can get the values of each one of them. Okay, fit C3 true. Now this is doing a completely different fitting. You could see number of observations is 116, strike rate less than 75. This is how the tree has created, right? Initially it has taken the strike rate less than or equal to 75 versus strike rate greater than 75, right? That's one. So when the strike rate was less than 75, There are 53 such kind of observations and they are all terminal nodes. Strike rate greater than 75. Again you have a position less than 3, less than or equal to 3 means batting in the top 3 positions where there are 47 such observations, and greater than 3 there are 16. So which means only the strike rate and the position at which he has batted are being considered for determining the win versus the loss in a C-tree 2 model. Whereas in a 3 model, a slightly more deeper, right, we are getting a 3 level depth, again strike rate less than 75 versus greater than 75, and within that greater than 75 again it worked out to, oh, it's only the two thing that has again come even when I have said it should be 3. So maximum depth is 3, but still it has considered the 2 scenario itself. Whereas when I'm going with C tree directly, unlimited tree, even there the result is the same. So in this case, the best possible result is coming only with the maximum depth of the tree containing the 3 terminal nodes, and the inputs that are deciding the tree are the strike rate and the position at which the person has typically batted. Now we can always do the plotting of these 3 variables. So we can only look at the 2 variable one now because depth of 2, because all others are exactly giving me the same solution as well. So when I'm doing this plot, this is how I can interpret the plot. Right, let me look at this plot. So strike rate less than or equal to 75, it's very significant. The p-value is 0.018, less than 0.05. So the split is a significant split. It can't be ignored. You have 53 observations here. If Virat Kohli bats at a strike rate of less than or equal to 75, there is almost a 60% chance that the team is losing the game. Whereas if he is batting at a strike rate of more than 75, and depending on at what position he is batting, if he is batting at anywhere in the top 3, there's almost 75 to 80% chance of winning, and even if he is batting in whereas there is a some percentage chance of a tie when he is batting in 4th or 5th kind of positions, anything beyond the 3rd position. So that's how this plotting is typically worked out. So let me see what all I have written as a part of the notes for it. Right. So the C tree, this part is clear. We are providing a data frame as well as the attributes. Loaded the party package. Get the data in the needed format. We have already got it. Preliminary inspection, because we are using the same data and the inspection for it has been done before the first model itself. I did not do it separately. Training data and the testing data, the splitting of it has already been done. Build the decision tree using the training sample. We have already done that. And use the controls with the maximum depth parameter to limit the depth of the tree. Here we have already created the depth of the tree to be 2 elements. And even if I have created it as 3 or some unlimited kind of stuff, still I have got only a 2-step tree for this particular example. We have done the plotting of the tree. So at each internal node, a p-value is reported, right? P-value less than, here it is 1.8%. Here it is 0.006, less than 0.05. So if it is less than 5%, which is true in both these cases, I see that that split is very much significant, and the split is giving me some kind of an additional information regarding the classification of the data. And as an additional information for the terminal nodes, for each of the terminal nodes, there is a bar chart that is being plotted. Right, this bar chart is showing that there is a high probability of a loss, whereas in these 2 bar charts, it's coming out that there is a high probability of winning the game. And instead of that, when we are using the model, if I type it as node, so which will tell me which node the observations end up in. And if I type it as prob, I will see, I will get the probabilities associated with them. So while trying to fit the model, C tree, I will type as node, which will give me which node. No, when I am trying to do the prediction, I have to do it. Sorry, this is not the case. Okay, now we are going ahead with the model using the prediction. Okay, let's go ahead with the prediction now. Pred underscore C tree. And I'm using the function called predict, right? That is what we would be going ahead with. So I'll take only the fit C tree true because all others are also resulting in the same kind of an input. The new data for me is test data, so we don't need to change all these things. Now this is where I can very well target out the type. I can set the type as response, which will give me what is the output, right? Whether this is whether each of these is going to be a win or a loss or what. Or in some cases, I can get it as which nodes, how many elements are there in each of the nodes, right? So this node 2, node 4, node 5, how many elements are there in each of the node. We can very well get that kind of an information when I'm giving it as node. But yes, with this response should suffice for me. So when I'm looking at what is coming out here, pred underscore C tree, it says some of them won, some of them lost, and so on. Now I can very well create a table. The first information being test data dollar result, that's the actuals. Pred underscore C tree, that's my predicted. DNN equal to C of actual comma predicted. So that's the table. So here it's working out that the accuracy of the model is 24 out of 50. So in this case, using this model, the accuracy is coming out to around 48%. So which means compared to the other two models for this kind of a data, the error rate is close to 52%. Even if I am using the maximum depth of the tree as 3 or 4 or 5 or even unlimited. And I could also look at a few important things. We did not look at the summary of the model. The summary of the model simply says it's a binary tree, nothing more than that. We have taken the plotting, we have got the predicted value, and based on the predicted values we got that the accuracy of the model is hardly 48%. So which means comparatively, compared to the other models, tree or C50 kind of algorithms, this model is not that great in terms of predicting the victory of the country based on the performance of Virat Kohli. So that's how we are evaluating this conditional inference classical tree model. Similarly, we have to look at the fourth and the fifth kind of models as well. With the same data set, we will look at them. Right, we'll try to get into the next one, which is the evolutionary classification tree. So something different regarding the evolutionary classification tree is, if you look at the three previous trees that we have considered, whether it is the tree algorithm from the tree package, C5.0 algorithm from the C50 package, or even the C tree algorithm, conditional inference classification tree algorithm from the party package, whatever are the three algorithms that we have looked at, they are splitting the tree based on the recursive partitioning method. That's the typical technique that is being used to partition the tree. So the tree is typically built using a forward stepwise search. And the split, whatever is the splitting criteria that is used, whether it is runs or score or strike rate, whatever the criteria that is used for doing the split, it is done with an objective of maximizing the homogeneity at the next step. So once it has done the split, I want the homogeneity to be maximized in the after the split has been performed. I want the values, more proportion of values belonging to one single class after the splitting process is completed. So there is a good chance that this kind of methods give us locally optimal results. Depends on where the starting point is. So depending on the seed value that we have used, there is a good chance that the best model or the best fitting split is purely based on the starting point that we have chosen for going ahead with the split. Whereas in case of evolutionary algorithm based trees, which is the current one that we are trying to look at, so there is a search that is going on the entire parameter space of trees, and instead of a local optimal result, we are going to get a global optimal result. So again, that doesn't mean that this is always better compared to the others, right? So there is no such kind of a rule which says this is better compared to the others. We have to apply all the kinds of techniques to our data, see to what extent the accuracy is improving when we are applying the same model on our test data. So till now we have got, for the data that we have considered, 58% to be the accuracy when we have worked out with C 5.0 algorithm. So this one works with package EV-tree, and the function is also EV-tree, which is nothing but evolutionary classification tree. And here also I have to give Z, which is the classes, the groups, the classification variables related variable, and categories related to the classification categories variable, and the data is all those that are going to influence that particular classification. So first let me install the package EV-tree, and we'll try to see what this EV-tree function is going to do in the process. Install.packages, I'll say EV-tree. So let me load this package also, EV-tree. So this is the package that is loaded. Now we'll use the same data set. So there are a lot of steps that I can very well bypass because all these steps are repeated. I'm loading the package, get the data, preliminary inspection is done, split the data into the training and testing data. All these are typically taken care of. Now I am building the decision tree using the training sample EV tree. So before I build it, let me see what it is containing. So learning of globally optimal classification. So there's a globally optimal classification that is being done, and regression. So I can use it for both the purposes using evolutionary algorithms. And the way we are giving the information is straightforward. I'm giving a formula, I'm giving a data. And if I have some kind of controls, I can very well specify the controls. Again, in the controls, we have few important things like the minimum bucket, which is the minimum number of elements that should be there as a part of the terminal node. So by default, it takes 7. But if I want to change the minimum bucket, minimum number of elements, I can very well specify it. Minimum split, if something has to be, if a particular node needs to be considered for splitting, there should be minimum of 20 elements. If I have to split it, the maximum depth, by default it takes to a size of 9, But if I really want to reduce it, it's better that I can reduce it to a certain number. Number of iterations that it should perform, by default there are 10,000 iterations that it is performing, and if I really want to play around with it, I can very well use it. Number of trees, by default it is taking 100 trees that are getting built. So there are so many such kind of things that are taken as default when an evolutionary tree is being built. Right? Lot of things are taken per default. So if I really want to change any of those things, I can very well play around with. Otherwise, I can take the defaults associated. So let me go with the default itself. Fit EV tree. That's the name of the model that I'm going with. And to go ahead with that particular model, again we have EV tree as the name of the function. Result tilde dot. Then the data we are calling as the train data, because that's the training data that we are using. If you really want a control to be set, right, you can very well set control equal to evtree.control. So you can specify any of those things that are there as a part of it. So let's say if I want to set max depth equal to 2. Now I can very well set it equal to 3, whatever. So from that purpose, let me again make it evtree2, right, where I have set the max depth equal to 2. Similarly, I'll set max depth equal to 3, or probably let me set it unlimited, right, 2, and okay, let me give 3 also, and at the same time let me set it as unlimited. So when I'm setting it as unlimited, I don't need to give this control at all. The system will coordinate the controlling part, and let me take it as EV3, fit underscore EV3. So these are the three models that I have. Again, I can evaluate the models by simply typing the name of the model. Okay, so here this is very clear. The first split is done based on opposition. So for Bangladesh, England, Ireland, Pakistan, if he has scored less than 21, then the chance is lost. Greater than or equal to 21, then the team has won. Whereas in case of Australia, Netherlands and New Zealand, if he has entered, if he has come to the crease when the score is less than 37, the team has lost, right, with an error rate of 16.7%. But if the entry score is greater than or equal to 37, so the first wicket partnership is almost 37 before he entered the crease, then I could see that the team has won with an error rate of 28.6%. So this is how the two model tree has worked out. I mean, the depth of the tree being 2. So opposition and runs and entry score are being considered for this particular model. Whereas when I am going with a tree depth of 3, it made much more worse. It went with a score of less than 303 versus greater than 303, and the runs being less than 22 versus greater than or equal to 22. Only that has been considered overall. That is what is the tree fitment of the tree for 3 as the maximum depth. Only 3 terminal nodes came up, and when I am going with infinite also is the same. So in case of 2, the situation is slightly different, whereas from 3 onward the situation is more or less the same. It ended up with just 3 terminal nodes. And when I am doing the plotting, I can do the plot of 2 and I can also do the plot of infinite. So I'll take these two cases. So in case of 2, this is how the situation is, right? Opposition, these are the oppositions here. and I could see the runs less than 22. So in case of this particular node, there is a good chance of losing the game with these oppositions, and he has scored 21 less than 21. Whereas if he scores more than or equal to 21, there is a good chance that the team has won. Whereas in against these oppositions, rather than his score, we are looking at when did he really come to the crease. Less than 37 runs versus greater than or equal to 37 runs. When he came to the crease, when the score is greater than or equal to 37, there is a good chance that the team has won, whereas on the other side, there is a good chance that the team has lost. Whereas the same thing, if I try to plot for an infinite tree, the situation is slightly different. Right, less than 22. So when the score is less than 303 and he scores less than 22, there is almost a 70% chance that the team has lost the game. Whereas if he scores at least more than 22, there is almost a 70% chance that the team has won the game. But overall, if the team score is greater than or equal to 303, there is almost a 75 to 80% chance that the team has won the game. So that's how I could very well see the visualization of this particular tree. And we have also seen which variables are contributing by typing in the name of the tree. You can also look at the summary of the model by typing the summary, wherein you are not getting anything important, so you don't need to focus on looking at the summary of the model. Now we can do the predictions of both the cases. So I'll take it as pred underscore fit evtree2. So I'm taking the predict function. Again, the model is fit underscore evtree2. That's the name of the model with which we are doing the fitting. The new data for me is the test data. The type in this case, I want it as response. I want to see which class comes into which. So this is the prediction for the tree of depth 2. Whereas tree of unlimited depth, I can very well ignore. I can very well take the other prediction. So these are the two predictions that are coming out. And I can very well go ahead now just to see what these predictions have come out. In the first case, these are the predictions, 1, 1, loss, loss, loss kind of stuff. So there are some loss, there are some wins. And even when I am going the other way also, 1, 1, loss, 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 1. So there are some kind of differences which you could see, because the last ones here, there are 2 loss, whereas here it's coming out to be lost versus 1. Now I can very well go ahead with the tables to try to understand the error rate of the model. So first I'll create a table with the actuals. The actuals are nothing but test data dollar result. That's the actual. The predicted value is pred underscore fit underscore evtree2. DNN is coming out as the actual versus predicted. So we are displaying a table. Wow, in this case the 2-tree model has given me a very good success rate of 33 out of 60 out of 50, giving me an accuracy of almost 66%. So this model is looking more and more appropriate for this data, right, which can help me in terms of predicting the chances of success, chances of victory for India based on the performance of Virat Kohli. Whereas when I am going with the other one, where I am considering the unlimited tree structure, unlimited depth of the tree, the accuracy is around 29. So 29 out of 50, giving me 58% only. So as far as up to this situation is concerned, the evolutionary tree has given me, the EV tree has given me an accuracy of 66% in terms of assessing the chance with which the country is going to win based on the performance of Virat Kohli. So let's see what that model is all about. Just for a quick understanding, I'll look at what the model is all about. Yeah, it looks at the oppositions. So for these oppositions, if the runs is less than 21, there's a good chance. So if he scores less than 21 versus greater than or equal to 21 against all these oppositions, versus when the oppositions are Australia, Netherlands or New Zealand, we are talking about the score at which he comes to the crease being less than 37 versus greater than or equal to 37, where the results could be quite comfortably understood regarding the performance of Virat Kohli. Right? Then, let me just quickly read through the stuff. So we have built the decision tree using the training sample. If possible, you can very well restrict the depth of the tree. We have tried first the maximum depth to be equal to 2, and in the other case, we have made it an unlimited tree by removing the controls altogether. So we got the details of the model by typing the name of the model. We have got the tree, plotting of the tree as well. We got the information, we got the decision rules in each of the cases. So in the tree we could see the number of observations and their distribution among the different classes. Then, yeah, we can use, so right now we have used the type as response, but I can very well use a prob to get the probability associated with each of the classes. So let me just showcase one for you. Predfit EV true, instead of response, if I type prob, and now when I look at the prediction, I could see that, okay, for the first person, there is a 80% chance that the team will win in this particular match. Whereas here there is a 71% chance that the team will win. 80% chance. So there are some cases where there is a 80% chance of win. There are some cases where there is only a 16% chance of a win. So when I am typing in prob, I get the probabilities associated with the victory. Right? So I can get the confusion matrix. We have already got using the table function. I can get the confusion matrix. This is the table function. I've got the confusion matrix, and based on that we have got the error rate of the fitting tree. And we can also change the depth of the tree. We have tried all those things. We can change the depth of the tree to 2, 3, unlimited. You can even go with the unrestricted model. But whatever is the kind of a model that we are going with, we are trying to test that model on the test data, and finally trying to see in which case the accuracy is much higher on the testing data. In this case, you have seen that if the depth of the tree is just 2, then the accuracy of the model went into a 66% when compared to when the depth of the tree is unrestricted. We have seen that the accuracy of the model on the test data has gone just to 58. There is a good chance of overfitting, but of course the tree got pruned directly, so there is no scope for overfitting happening on this data here. So this is how the evolutionary classification tree works. The main thing that you have to understand regarding the evolutionary classification tree is it is using a global optimization method. It's not a local optimum that is being used for the construction of the tree. So there is a good chance that the variables that were not considered at all earlier might come in as the most significant variables when we are using this evolutionary classification tree algorithm for creating the decision tree. Alright, now let's move towards one more important classification tree algorithm, which is otherwise called as oblique classification tree. So till now, the 4 algorithms that we have considered, they all used axis parallel split. When I say axis parallel split, they have taken only one variable at a time. Let's say runs less than or equal to 21. Or they have taken a position equal to either Australia or New Zealand or something. So at any point in time, for doing the splitting, only one variable was considered and a rule is developed on that one single variable. All the four models that we have looked till now. So these models, they have produced the binary partition trees. They have done the partitioning by considering axis parallel split of all the attributes that we, based on different attributes that were provided to it. It has taken one attribute at a time and it has created the rules based on that specific attribute. So only single attribute was used to create a rule at any point in time. Whereas in oblique trees, we are not going with axis parallel split, which means we are not looking at only one single attribute to create a rule to split the tree. We are using oblique splits. So when we are talking about oblique split, instead of taking one attribute at a time, we are considering the weighted combination of attributes to do the splitting of the tree. Right? So it may come out that, okay, 0.5 times the runs less than or equal to 21 plus something something, right? Probably plus 0.25 times the strike rate less than or equal to 75. So such kind of a weighted combination of the attributes is typically going to be used in the oblique tree mechanism. And that can be implemented through a package called oblique.tree, and we have a function also called oblique.tree. So we'll use that particular package and the function to execute this logic. So we will first install the package oblique.tree. We can also load the particular package, library oblique.tree. So the package is loaded. Now we can see what is this oblique.tree. An oblique tree is grown binary recursive partitioning. Again, this is not using the this is also an optimal local optimal kind of a solution. It is not going with a global optimal. Using the response in the specified formula, the only difference here is it uses oblique splits instead of axis parallel split. And oblique split is nothing but linear combination of the terms. Instead of taking only one term at a time to create the split, it takes a linear combination of the terms to create the split. So formula wise, function wise, yes, one I have to give the formula. I also need to give the data. If I have to set the controls with respect to the size of the tree, the maximum depth of the tree and all, I can very well set the same. The method, I'm here, the default method is the recursive partitioning. Otherwise, we can go with model frame. One of the two methods can be specified. Split impurity also, the splitting procedure, I can very well go with either deviance or Gini kind of procedures. One of the two, just like the tree algorithm. Oblique splits. Here, I can specify only. When I say only, it is only oblique split. When I say on, it means it could be oblique split or even an axis parallel split. And if I say off, it's only axis parallel split. So the default, I may have to set it to either only, because we are considering, if I say off, then it is same as your tree algorithm itself. So I don't want to consider the off. I will typically look at only here. Probably I can try one using the deviance, the other one using the Gini. So that is what I can do. right? So now when we look at something more regarding this, okay, we have the classes, we have the data, the control I can very well specify, especially the maximum depth and all those things. The split impurity also I can specify whether I want a deviance or a Gini. We will try both of them. And coming to the steps of the implementation, we are loading the package appropriate. We have already loaded it. We got the data. We did some kind of inspection, split the data into the training data as well as the testing data. Now let's go ahead in terms of building. So if you want, you can build the tree using all the attributes, or you can very well use only a subset of them. We have 10 attributes in our data. So if you want, you can split the tree using all the attributes, or you can use only a few of them. So let's go ahead by taking all the attributes again. Right, I can very well go ahead in terms of using all the attributes. So let me call it as fit underscore oblique tree underscore deviance. I'll use the deviance algorithm here. So we'll use the function oblique dot tree. The input for me is the result tilde dot data. I am giving straightforward train data, which is my training data for this particular purpose. Then oblique dot splits, I will set it to only, right, so that I'll get only the splits related information. Otherwise I can set it to on or off depending on whether I should consider even the axis parallel splits also. And the control also, if I want, I can very well set the control where I am setting tree dot control. In this tree dot control, first I have to give the number of observations, which is 116 in this case, and I have to specify let's say what is the minimum that goes into each one of them. So minimum cut size, let's say we will set it as 10. And apart from that, it also requires split dot impurity, wherein I can very well specify either deviance or Gini. So because the first one is deviance, I'll consider it as deviance while splitting the tree. So this is the model. Yes, it has done the job. So we have an oblique tree considering the deviances. Similarly, I can have an oblique tree considering the Gini. Right, so I can very well specify it as Gini, all others remaining the same. I did not specify the maximum depth of the tree, I specified the minimum cut should be at least 10 Gini. So even this model is getting fit. So let's evaluate these two models. So the deviance model here, wow, this is the model. The model is saying 2.34 minus 0.01 times score, minus 0.53 times innings, plus 0.02 times runs, minus 7.58 times proportion, blah 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 blah. This whole thing is working out in terms of winning. So there is a 70% chance that the team is going to win. But if this whole value is greater than or equal to 0, wherein 39 such occurrences are there, there is a chance that the team is losing, where there is a 64% of those occurrences have resulted in a team losing. Similarly, now you could see the status within it, right? The status is not out kind of stuff. So here we don't have a better scenario in case of status, but again it is showing there is a 63% chance of winning. Again, one more equation is being formed internally where there is a 70% chance of winning. And again, the oppositions like New Zealand, Netherlands, Sri Lanka are being considered. So the model is slightly complex here. right? But what is very important is if I'm testing it on the test data, what is the kind of a result that is coming out? Rather than the explainability here, I would like to look at what is the kind of predictability that is associated with this model. Even when I am going with the Gini, again a slightly different, I don't think any slightly different observation, probably in this case also more or less a similar kind of output has come out. So both the Gini as well as the deviance are resulting in a similar kind of output out here. We are not seeing anything big different in the kind of output that we have got in both the cases. But okay, let's do a plotting now. Right, doing the plotting of this particular tree. Oh, this is the plotting of the tree. This is how the tree got, and we could also create the text with respect to this. So this is how the tree got split. 2.34, this entire value is less than 0. And this is how the whole thing, so these are all the nodes, leap nodes where the winning is there. These are the nodes where the losing is there, and that's how the things have gone further. So that's how the model got built. The explainability of the model is slightly weaker because it's not an axis parallel split. It's a linear combination of the various attributes that have been considered that has gone into the classification of the data into the win versus the loss. And I could also look at the summary of the typical model. So the summary is saying that there are 8 terminal nodes, right? The variables that are typically used in the construction is status and oppositions. Pre-construction, these are the ones that are typically being used. I could see that the residual mean deviance is 1.267, slightly on the higher side, but this is something that is phenomenal. Misclassification error rate is 0. So which means all of them are classified quite correctly. But this is where the possibility of the overfitting can come out. We could clearly see that this misclassification rate of 0 means even when I am doing it on a real data, it might have, if it comes out on my testing data, if the error rate is coming out close to 0, then I can trust the model quite heavily. Now, this is giving me a big different impression altogether. On the training data, this model is 100% accurate, but what is the level of accuracy it carries when I'm taking it on to my testing data? Here the misclassification rate is quite astounding. It's very much 0. Now this is where I want to take a prediction, but let's quickly look at some of the things here before we go towards the prediction part. You estimate the tree, allow only oblique splits, so we are considering only obliques, but if I am setting it to on, then both oblique as well as axis parallel will be considered. If I am setting it to off, only axis parallel will be considered. Then we are using a tree dot control where I can specify the total number of observations, 116 here. Minimum number of observations that should be there in the node, I have set it as min cut equal to 10. Right, probably I can very well grow the tree. If I want to grow the tree even more further, probably I'll set the min cut to be slightly on the higher side. Visualize the details of the tree using the plot. We have done that. We have visualized the decision rules. Typing the name of the model, we got the full details of the tree. Even the summary, we got some important information regarding the misclassification rate, residual mean deviance, etc. Now I'll go ahead towards the prediction part. So I'll say predict underscore fit oblique score deviance. So I'll use the function called predict, where the model that I'm using is fit oblique tree deviance. The new data for me is test data, and the type for me in this case I'll give the class. So I'll get the class of each of these. So if I look at what is typically coming out, for each of these 50 elements. So it's coming out that last, almost everyone is coming out to be the last as a part of this model. That's looking pretty pathetic. If I'm using this model, it looks like everyone is getting into the last category itself. There is not even a single win in when I'm going with this model. So this is an indication of overfitting of the tree altogether. Right, so I can very well use the table where I'm using test data dollar result. That's one thing, and I'm also considering the predicted values, which is the pred underscore fit oblique tree deviance. Then I'm setting dvnn equal to the c function of actual comma predicted. So we are getting a table where only 19 is accurate. So the accuracy of the model looks like 19 out of 50, which is only 38% in this case. So though the model has become very complex, it has not actually improvised the accuracy of the model, whereas on the other side it has worsened the accuracy of the model. It's only 38% accurate, which means there is no need to typically consider this model. So overall, if you see, one either a C50 algorithm has done a 58% accuracy for this data set, or even the evolutionary classification tree where we are able to generate a 66% accuracy on the test data. So these are the two things for this particular data set have created some better kind of result. So if we want to use it for the further prediction purposes on a new data, it's better that I use any one of these 2-3 algorithms typically for assessing whether India is going to win a match given the performance of Virat Kohli in that particular match. So that's how we can look at the different classification trees using different attributes. How do we classify the data into different groups? So these are the different kinds of classification trees that we have looked at in this session. If you have any further queries regarding any of these different trees, please feel free to get back to me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.